Okay. Let me check something. Okay. Okay. So today is session number 21, I guess, of the second semester on braided fusion category. 21. So finally, yes, last week we started the section we are the most interested in this class since 2 semesters. So we started this class mainly for this section, the core of a braided fusion category. So remember that this notion of core of a braided fusion category, it's a way to extract the non-group theoretical data from a category, and it is so you need to choose a maximal Tanaka subcategory, but in fact we will show that it is independent of the choice up to some isomorphism. And the core is what is we will explain to be weakly anisotropic, which means it's a weak version to have no Tanaka subcategory, but in fact, as we will see, the core of the core is anisotropic. So the core of the core has no Tanaka subcategory except VEC. So that's very convenient. Lattice. So we talk about modular lattices because in fact we will need. So we will use this lemma regarding modular lattices. So the lattice of fusion subcategory. If the Grothendieck ring is commutative, this lattice is always modular, and in fact it's true for every commutative fusion ring also. So the proof is there. So yeah, last week I explained some fun facts about lattices. I will not recall here. I remember I was a bit confused about what was the pentagon sublattice here. And in fact, I draw the pentagon sublattice. Okay. So this lemma recovers some result. So we know that the normal subgroup lattice is modular, and yeah. What else? In the abelian case, the subgroup lattice is modular, and in general, the normal subgroup lattice is modular. And yeah. Okay. So maximal Tanakian subcategory and the core formulation of the theorem. So let E be a Tanakian subcategory. Tanakian subcategory braided fusion category C. And let F from E to VEC be a fiber counter. So by some previous section, we know that this data permit to determine the fiber category. This data determine fiber category. Muger centralizer of E, tensor over E, by Vec. So the disequivalentization of E prime, which is a braided fusion category equipped with an action of the group so this one, remember, this is the disequivalentization by GF. So this action can be restated category in a categorical way. So equivalently, there is a monoidal functor GF2 so here it's by this notation we denote the category associated to the group. To remember what is the definition of an action of a group? In fact, an action on the braided fusion category. So that's why you need the braided automorphism here. And then you get a group homomorphism when you really deal with the group and no more with category. So this functor implies a proper group homomorphism. This is denoted 106, where so this is just the group of isomorphism class of object here, where OBR denote the group isomorphism class C of object in the braided autoequivalence category. Autoequivalence category. So this notation. Okay, so yeah. You can again maybe see this as an overkill. You just maybe you can say okay, we identified that with the group, and but anyway. So now, you have this this group homomorphism here. So what act is this group? So in fact, the image of that here completely determines the action of the group. In fact, it completely determines the action. Completely determines the data we need. Maybe this may not be injective, I don't know. So maybe the image do not completely recover G, but at least it recover all the data we need. So the image of GF is exactly what we need, the data we need. So let gamma EF be image of 106. And in fact, we only need this group. So the Tanakian subcategory is maximal if it is properly contained in any other. It is not properly contained in any other Tanakian subcategory. So as you can expect, Tanakian subcategory I in C is maximal if it is not properly, as you can expect, contained in any other Tanakian subcategory. Okay, so let the definition, you take C to be the braided fusion category containing E. So let C and E as above. So above. So E est un subcategory, the braided fusion category. So let E and E be as above and assume that it is maximal. So the pair, so this disequivalentization together with this group, the image of the GF, is called the core of C corresponding to E, and is denoted. So this is this. We will show that it is independent of the choice of the maximal Tanaka subcategory. But for now, we denote it. Before proving it is independent, we denote it with this parameter. So we will show that it's independent of the choice. So in section 542, we prove the following result. So saying that it is independent, but in fact, in this section, we will prove something a little bit more general. Let C be a braided fusion category. And let E1, E2 be two maximal Tanakian subcategory of C with fiber functor Fi from EI to vec I equal 1, 2. Then the core with respect to E1 F1 of C isomorphic to the core of E2 F2 of C. So remember that the core is defined as a pair. So we need to specify what we mean by isomorphism. And this is exactly what we will explain now. So this is, I guess, you can think this as one of the main results of the entire paper. This one and the fact that the core is weakly anisotropic, or the core of the core is anisotropic, which means there is no more group theoretical data. At least there is no more Tanakian data. But you can still get a symmetric fusion subcategory, which is not Tanakian. But at least there is no more Tanakian thing. In fact, how to condensate, you can condensate Tanakian subcategory, but how to condensate super Tanakian category, that's an issue. That's why we are, it's not clear that we can really condensate super Tanakian in some way. As we will see, in fact, later, there are three classes of weakly anisotropic braided fusion category, one ordinary class, one super class, and one Ising class. And the super Ising class involves some SVEC inside. Anyway. Okay, so what about this 107 meaning? The precise meaning of this isomorphism is as follows. Let this is a fiber category. Fiber category associated to the fiber functor I equal 1, 2. Then so what the meaning of this isomorphism is that there exists a braided tensor equivalence, H from this fiber category to the other. Not only that, this braided tensor equivalence should induce a group isomorphism between the group of braided autoequivalence, which map the group of the first pair to the group of the second pair of the core. So whose induced group isomorphism H star from that to that maps this group to this group. Okay. So this is a definition of this isomorphism. So this is more or less what we need to prove. But as I said, we will show something a little bit more general. So what this theorem is saying, this is saying exactly what I said before. It expresses the independence. The theorem 5.9 shows that the equivalence class of core is in fact independent of the choice of maximal Tanakian subcategory. Subcategory in C. That's why we can refer to the core, not a core. So we refer to it simply as the core of C. And denote it just core of C. There is one equivalence class. There is a single equivalence class. So remark. So what about that? Okay, so this remark is about we've involved braided G-crossed. So in this remark, we will explain in what sense you have several possible actions which align action coming from braided G-crossed model and action coming from something else. So remark. Then let C be a braided fusion category. And let E equal red G be a Tanakian subcategory. Recall that the déséquivalentization C index G carries the structure of a braided G cross category. It carries the structure of a braided G crossed category. See section 4.4. So by proposition 5, no, by proposition in previous section, point number I, the fiber category identify with the trivial component. So remember that braided G cross come with three ingredients, a G grading, a G braiding, and a G action. And here we are talking about the trivial component of the G grading. So remember that we proved that the fiber category is identified with the trivial component of the G grading from CG. In addition, the G action on this fiber category agree with the G action coming from the braided G cross. We've agreed with the G action on the neutral component of the disequivalization coming from the braided G cross structure. So in particular, in the case that E is maximal, Tanakian subcategory E is maximal, then you can define the core, because remember that we define the core only in the maximal case. Then we can define the core, and in fact, this core can be completely described in terms of the braided G cross category. So I'm not saying that it is equivalent to that. I'm just saying that from the data of the braided G cross category, so G grading, G braiding, G action, you can completely determine, you can describe the core. The core can be described completely in terms of the braided G crossed category. CG. So all the data are there. I mean, here to describe that you need E and F, C, E, and F, in fact. But if you have the data of a braided G cross, this data is enough to recover exactly. So yeah, to define that. You have all the required information. Yeah. Okay, so how to prove that? Proof of theorem 5-9. In fact, as I said, we will prove something a little more stronger. we will prove the following statement, which is actually stronger than theorem 5.9. And in fact, so this theorem, the proof of this theorem 5.11 will involve modular lattice. So the proof is quite conceptual. So it's nice. Let's see the braided fusion. So the beginning is the same, at the end, in fact, E1 and E2 will not be maximal, but they will just be maximal in the category generated by E1 and E2. That's the slide variation, the slide generalization. Let's see the braided fusion category. And in fact, it will be more convenient for the proof. I in C, I equal 1 to B Tanakian subcategory. Equate with fiber factor Fi from I to Vec. Assume so they are not maximal, but maximal in the Tanakian subcategory. No, among the Tanakian subcategory of the fusion subcategory generated by E1 and E2. Assume E1 and E2 are maximal among the Tanakian subcategory of the fusion subcategory generated by E1 and E2. Then you get so isomorphism 107, so which we write explicitly. Then there exists a braided tensor equivalence. H from this one to this one such that so induced group isomorphism maps as before, such that the induced group isomorphism H star from this group graded autoequivalence to this one maps this image, this group, to this group. Okay. So how? So this is the theorem. So now the proof. So the proof will be given as a discussion. In fact, there will be no formal proof. So to construct the equivalence, constantly equivalence 108. So this one. So we first need to construct that, and then need to check that. So how to make that? We will consider some intersection. Choose a fiber functor f from the intersection to vec such that compatible with the restriction and the given fiber functor of E1 and E2 together with isomorphism between the restriction F1 restricted to that, F2 restricted to that, and F itself, so each from that to that. So as an exercise, you need to show that it is possible. It's always possible. It always exists. Such a fiber functor. Okay. So now you consider the induced group homomorphism. So this induced epimorphism from that automorphism of Fi to automorphism of F, which is GF I equal 1, 2. Okay, so you have this kind of, so the fiber functor both restrict to F, in fact. So you have this epimorphism of the group of automorphism of this fiber functor. Okay. So now, what should we do to get this, to make this H? So the rest is more or less canonical, but we will still explain the remaining part of the construction. Is canonical. So, in fact, remember that you can, we discuss, where is it? In corollary 436. That you have the fiber category, how the fiber category deal with some intersection. So we have a result for that. And so, thanks to this result, I will recall, we can identify each pair of fiber functor And that's for each pair of core. With the pair for the intersection. Because in fact, in the intersection, when you condensate, in fact, it's the same as condensating a big thing or condensating a small thing in the intersection. There is no. We already discussed that. So with the pair two avec gamma U1 to F. So 110. Okay. So this last pair is called 110. So how do we identify this with, for example, when I equal 1? Identify 110 with, for example, you can choose I equal 1, but of course, this is the same thing for I equal 2. You just need to prove the following, because what we need to prove are the assumptions we need to apply corollary for 36. And I will explain how to recover the former assumption of the corollary, how to identify, in fact, this with what was written in the corollary. So you need to prove that and to prove that. So intersection 2 generate E1 is E1. It suffices to prove by corollary for 36 2. So when I say suffice to prove that by this corollary. And in the framework of this corollary, you have this right as in the framework of the corollary. So let B1E from this corollary. So we for the statement of this corollary. So this is D1. This is E. So the intersection of D1 and E is equal to that. And this is D1 again, D1 of E is, and in fact, as long as you have this, which is the assumption in the corollary, you get this. Oh, so it's time for the pause. So pause. Okay. So as I said, to prove that we can identify this and this by this, you need to show that, because with that you can apply this corollary. And in this corollary, you have D and E, for D1 and D, and the D1 is this one, and the E is this one. And as long as so in fact, this is immediate, and then you have exactly what we need. So we are reduced to show this. As long as you can show this, you can apply this, and you get this automatically. Immediate by this identification and corollary, and corollary, and this corollary. Okay. Okay. So now why these two identity hold? This and this. So let's call this one A and this one B, because we will need to call them later. So by this corollary, so as I said, so this corollary is enough to show that. So these identities A and B imply by the existence of a G equivalent braided equivalence with G equal gamma E1 F1 equivariant braided equivalence E1 prime equivalent. So exactly what we expect. And so an equivalence between, yeah, it's a little redundant. And so the expected equivalence between this pair and the pair is 110 here. So yeah, just what we need to prove. So as I said, what remains is to prove these two identities, A and B. So denoted together 111. It remains to prove 111. So clearly we have, so to get the identity A, we have something weaker, which is immediate. E prime intersection E1 prime intersection E2 prime intersection E1 is equal to E1 intersection E2 prime. So that's immediate. So let's call that A prime. So remember, A is, so in A, here is E1, E2. What is immediate is when you have E1, E2 prime. So why this is immediate? Since E1 is included in E1 prime, if E1 is connected. So E1 intersection E1 prime is E1. So here you have E1, E1 prime is E1, and they remain E2, so it's immediate. Okay, next. By the lemma 5.6, so the lemma involving modular lattice. Modular lattice. Modular lattice. What do we have for immediately? We get directly that E1 prime intersection E2 prime with E2 is equal to E2 prime with E1 intersection E1. So remember to get such an equality. So let me come back. It's not so far. Where is it? Yeah. Yeah. What we need is, so this is the kind of equality identity we wrote, but what we need is, first we need that. So let me show you what is D, what is A in our setting, and then you will get automatically this, because yeah, the relation is only on A, D, and A. The other one are just random. So you can just, so you have that with, since E1 is included in E1 prime by Tanakian, and this corresponds to, so maybe I should write another color for it. So since E1 is included in E1 prime, which correspond to, in the lemma, this is E, this is A. So this is D here, this is A. And AB are more or less like that. So it's immediate. This one is called B prime. So A prime is almost A, B prime is almost B. So we just need, yeah. In B prime you have that, which is that. So we need to show that this one equals this one. Okay. And in fact, we need to show exactly the identities in the following lemma. Now we use the following lemma. So lemma 512 if E1, E2 included in C are maximal among finite subcategories of E1 and E2, but generated by E1 and E2, which is the assumption of the theorem phi 11. Then E1 prime intersection E2 equal E1 intersection E2 prime equal E1 intersection E2. And together, if you have that, wait, let me write, yeah. Together with A prime, you get A. I will show you. So this is identity 112, and the other identity. So the category generated by E1 and E2 prime is a category generated by E1 prime and E2, which is a category generated by E1 prime and E2 prime. And this, together with B prime, you get B. And that is 130. So why I am stating that? So A prime is that. So we have A prime here. So what do we need for A? We don't want this prime. Yeah. So in fact, you have this, which is there, which is equal to that by this, which is exactly what we want. So A prime, which is true, it's trivially true together with this lemma, you get A. Now what about B? So B, so you have this equal this. So we already have this equal this. So we need to show that this is equal to this. So we need to show that this is included in there. Some sense. So what? So here you have that, which is this one. This one. Is it in the good order? Yeah, does not matter. Yeah, wait. Let me check. Wait a minute. Just checking. 5, 6. Yeah, it should be okay. Okay, so you have this, which is equal to that. Okay. And so you have that. But this is trivially included here because this is generated by that and that. So when you intersect that, of course, you get this only. So this and B prime imply B. You get that only because this is included in that because this is equal to that, which trivially contain E1 prime. So we are just, so now we are reduced to prove this lemma. So the main result of the paper reduce now to this lemma. Okay. So first observe that the fusion subcategory E1 prime intersection E2 generate and you generate E1. So E1 generate, so subcategory generated by E1 and intersection of E1 prime and E2 is a Tanakian. So this is Tanakian subcategory of E1 generate of the subcategory generated by E1 and E2. And of course it contains E1. So this is clearly Tanakian because this is Tanakian. And here, E2 is Tanakian, but you only keep the E2, the part of E2 which, how to say, which, I forgot how we say, it's not commute because we are not in algebra. Yeah, which is in the center, but I forgot there is a name for. Yeah, Google Center. But there is a name for saying an object which centralized, yeah, centralized. Centralized. So we are just taking the element of E2 which centralize with E1. So what you get is symmetric, and because it only involves E1 and E2, it's also positive, so it's Tanakian. So you can see that as an exercise. So it's a Tanakian subcategory contained in that. Okay, but by assumption, E1 is maximal in E1, E2. Yeah. And so because by maximality, in fact, this contains that, and this is maximal, so you should have an equality by assumption. Hence, must equals E1. And this is not the exercise. By maximality. So this is immediate. Maximality. So, so what do you see? You see that this equals this, which means that adding that has no effect, which means that this is included in that. This implies E1 prime intersection E2 is included in E1. And therefore, yeah. E1 prime intersection E2 is included in E1 intersection E2. Yeah. Very trivially, because you can say which is equal to E1 prime intersection E2 intersection 2, which is equal to E1. Which is included. E1 intersection E2. So we have this inclusion. Now, so similarly, you have also for you have the inclusion for so wait. So you have this inclusion. So wait. No, I guess we can directly show it is. You can directly show it is an equality, and therefore you have E1 prime intersection equal E1 intersection. So the proof is you can directly get the proof as follow. So E1 prime intersection E2 is included in E1 intersection E2, as I said. So wait, let me write this. This is equal to 1 prime intersection E2 intersection E2 included in E1 intersection E2. Okay. So this is included in E1 prime intersection E2 because E1 is included in E1 prime by symmetry or by Stanakian. Because it's my it is just the symmetric assumption. By symmetric assumption, in fact, Stanakian. Here is Stanakian. In fact, you only need symmetry to get this inclusion. Yeah. So you get this equal this included in this, but look, they are the same here. E1 prime intersection E2, E1 prime intersection E2. So they are all equality everywhere. You have this. This and this are equal. So you have equality everywhere. So equality everywhere. In particular, E1 prime intersection E2 equal E1 intersection E2. Okay. So, which is 111. And you get the same for I equal 2. So the identity E1 intersection E2 prime equal E1 intersection E2 is similar. Follow similarly. So we get 112. Now, what about 113? Finally, 113 follow from 112 and the double centralizer theorem. The double centralizer theorem. So here it's called corollary 311. Oh, yeah. In fact, there is a typo. There may be a typo in the paper because here they cited theorem 310.2, 310 second point, but in fact, I guess, unless I am mistaken, what we really need to apply is this corollary. Otherwise, you have something else to prove, but it's okay. This corollary work. So what about this double centralizer? So remember, what this is saying. So B included in T implies B double centralizer equal B C prime. Something like that. Okay. The theorem is when you assume that C prime, centralizer of C is included in D. But in fact, here we don't need, and it's not clear. It's true, but we don't really need. So the double centralizer here corresponding to here you identify with E1, and this one is E1. So what you get is okay. So now the proof is as follows. So you have E1 prime intersection E2. So we know this identity. So we want to apply these identities to apply the Muger centralizer to get that. What we need to care about is this double centralizer here. So this is a double centralizer and this one. And here you apply the double centralizer theorem. To get E1 and E1 intersection E2 prime and E2 prime. I guess. Yeah, so this one, this is just that, and this. So you have double centralizer. So you have this is D, and C prime is that. Okay, but now this is just equal to E1 and E2 prime. Why? E1, E2 prime. Because, yeah, this is included here because you have intersection with that. So you can, because you generate, you can remove this one. You don't need, so you directly get that. And so because of that, you can get, so you have reapplied, which one? This one. So you get, you get this equal this. Yeah, so that's all for this proof. Yeah. So this complete the proof. So you see this proof, much easier to follow. And this is the main theorem of the paper. One of the main. The other main, in my opinion, is the fact that the core is weakly anisotropic. And the core of the core is anisotropic, which means there is no, as I will define later, there is no good theoretical data in the sense of Tanaki. There is no Tanakian subcategory except vect itself. Okay, so the next remark and the next theorem the next remark, we will go a little bit quickly for the next remark because it's just a generalization of the theorem, but we will not really need. So I checked, in fact, it was not used elsewhere. So it's just a remark that we can prove something more general, but we don't need to spend too much time. It will not be used later. So let's go quickly. Let's go. Suppose in the setting, it's a little generalization. Theorem 511. That's very fusion subcategory. C tilde included in C containing E1, 2, E I prime tilde to be E I prime intersection C tilde denote so gamma tilde E I denote the image of the homomorphism from GF to hot top. E prime E tilde EI. So it is straightforward to verify. We get something similar to, yeah. To be honest, I don't know the motivation for this remark. And in fact, same thing for the next subsection. I did not write any motivation, so it's a little bit more general. So maybe we can get something else, some application, but I did not mention it. So verify that the equivalence 108 constructed in the proof of theorem 511, so 108. What was it? Yeah, the H, just the H. Induce to verify that the equivalence induce and equivalence H tilde from this this With the same thing when you have the induced group isomorphism maps the group to the other group. Induced isomorphism H star tilde OPR. This one back to tilde prime 2 maps this one to this one. And fit. There is something new here. Here you have a commuting diagram and fit into the canonical commuting diagram. So gamma E1 F1 H star gamma E2 F2. And here you have an epimorphism. Gamma E1 tilde 1 H star tilde gamma E2 F2 tilde. And the other epimorphism. Yeah. So this is our epimorphism. Let me put a question now because that's not specified. Because I don't see motivation for that right now. I don't want to spend too much time. So C till included in C containing. Okay, so it's just a restriction. So you can apply the same result. So you have the result for C and E1, E2. But if you have a C till in between C and E1, E2, you can, in fact, you can directly take C till equal that. Why not? And then you have just theorem 5.9, because then it will be maximal inside. But if you get something in between, you get this kind of restriction, and you get, yeah, you get the same kind of, I want to say, of equivalence of pairs of core. So in some sense, the core. So this theorem, wait. Yeah, in fact, in the theorem 5.11, you don't speak about core. You just explicitly write this equivalence. Anyway. Anyway. Yes, the motivation is missing for this remark. So this follow because gamma tilde Fi is the image. Oh yeah, here you have a very, very long sentence. Image of gamma Fi included in So this is there. When you read this sentence, maybe you believe that the author wanted to follow a challenge to write the most complicated sentence possible, because it's really complete. So the image of this subgroup under the homomorphism. So this I'm not even sure. I'm not making a mistake. To this. Okay. And okay. And so what? Here. So is it just so let me check if I did not miss something. Yeah. Yeah, so yeah, the notation it may not be automorphism because we are not the same. It should be isomorphism. That should be isomorphism, I guess. Automorphism means the same thing, but we are not in the same thing. So this is the first typo, I guess. And this, yeah, it's confusing. I don't want to. I just mentioned because it was written in the paper, but without any further motivation, I don't see why we should spend much time on that. Isomorphism. This is a group of, yeah, maybe there is a typo here again. Is the group of isomorphism class of braided to equivalence. Isomorphism classes braided auto equivalence of E. Maybe that's why I wrote this notation. Okay, so let me come back. Of that, reserving yeah, so okay, this notation with hot was just a notation. It was not just really an automorphism, but we need to understand this like that. The group of isomorphism class of braided to equivalence of that, preserving that, included in that. So really confusing. This sentence should be simplified. This is too complicated. Anyway, so don't need to care much about this remark. In fact, we will not need. I just mentioned, I guess it took too much time. And yeah, so the next subsection we'll do tomorrow will be a little bit similar. Again, this will be something a bit complicated, but that we will not need later, but maybe less complicated by the remark, but still a generalization of theorem by the 11. This will be similar to this remark. I'm not even. I'm also asking whether this subsection is essentially the same as the remark. In fact, it's not clear from another point of view, but anyway, we will stop here. So tomorrow we'll start with that, but it will not take too much time, so don't worry. And then we will. So I will just mention that because it's mentioned in the paper. So it will be quick, and then we will start the subsection 5.5, the properties of the core. So an interesting theorem about non-degeneracy and the weakly anisotropic property. And that's really, really important. So don't worry about this remark and this section 543. We will not need more later. Okay, so see you tomorrow. Ah.